feeling today? Woohoo. Before we dive into the new unit, I want to review briefly the results of the unit test. And I'm curious, how do you guys think it went? Maybe we compare it to the first unit test. Part A, better average, lower average, or do you think you stayed the same? Better average? Anybody else? Agree, disagree? Sorry, I had a typo on this. You feel like you have no way to know? Do you just base off of how you felt yourself in the test? Yeah? Do you guys remember how well you did on Unit 1 test Part A? Very, very high, 93% average. So, no pressure. But again, do you think you stayed here as a class? Do you think you went up, or do you think you came down? Do you think this unit had harder objectives than the first one? How much? A lot? I think we stayed went to an A-, B+, B. We came down to an 86, which is a solid B. So the multiple choice, which again is 2 attempts, was trickier this time, right? More challenging. The concepts are getting a lot more involved, that's for sure. You had to name relationships, you had to pick descriptors, you had to assign chirality. Remember those questions I gave you that were saying, is it R, is it S, is it neither, is there not enough information? Some of you saw those questions on there. You had to name functional groups. And that can really trip people up too, because they forget that an amine is not inside of an amide. They forget that an alkene is not inside of an aromatic ring, things like that. Part B, Unit 1 test. You guys remember how you did? B+. Up, same, or down? Yeah? It would make sense that it would trend down, right? Like if the multiple choice was challenging after having a chance to review and study the same question type, then the part B is almost always harder because the right answer is not in front of you. And these were a bit challenging. It was, one of the questions was very open-ended. Draw something, make it work, right? That's really a challenge. So this one, do you think it came down the same? We went 6% from Unit 1 Part A to or 7% from Unit 1 Part A to Unit 2 Part A. 7% again? Or do you think this one hit harder? Or do you think it was closer? 83. This one hit harder. 76 average. That's a solid C. So averages on this unit test were B for Part A, C for Part B. Do you guys know how far we are from the midterm? Yeah, like 2.5 weeks. 2 weeks from today, we'll be having a review period. And then 2 weeks from Wednesday, you'll have your midterm. So what are you guys going to review? Part A materials or Part B? I'm sorry. Unit 1 material or Unit 2?
That's a trick question. You should review all of it.
Good answer. That was a trick question. But I do encourage you to find the questions you struggled with in Unit 1 and study those. The questions that you did well in Unit 1, you'll probably continue to do well with. Bond line is getting more and more familiar with all of you. So make sure that you understand bond line well, but don't waste too much time trying to study all of that. Study things like enantiomers, diastereomers. Study things like chiral carbons, chiral molecules. Study your functional groups. You guys know that I'm in an Arabic class this semester, and over the weekend I spent time writing out flashcards because I have a vocab quiz tomorrow. And I'm encouraging you guys to find time to make flashcards for your functional groups. But don't just make any flashcards. Maybe find something that is meaningful to you. Because remember, functional groups show up in huge molecules so they can look really different given just small changes to a structure. That's why on the functional groups chart that I give you a generic form so that you can pick it out anywhere, and I give you an example where it's applied so that you can get familiar with seeing it in context. All right, any questions on the unit test? All right, we've got 2 molecules on the board. I'm not expecting you to name them, but their names are actually not very hard. Cyclohexanone and I don't know, whatever that is. It's an ether. Oh, and I drew it wrong actually. I've got too many carbons in it. It's not just an ether though, is it? What else has it got going on? Two sets of carbon-carbon double bonds. Yeah, which we call alkenes. What is the relationship between these molecules? Are they identical? Are they constitutional isomers, structural isomers? Are they stereoisomers? Enantiomer, diastereomer. Are they not related at all? Are they just unrelated chemicals? Decide in your groups, what's the relationship? How would you answer it? What is the relationship? What is the relationship? How would you find out? Are they structural isomers, stereoisomers? Are they identical? Are they not related? What do we call that? The number of all of them. The number of all of them. Like the number of carbons, the number of hydrogens, the number of oxygens in the molecule. We call that. It is really easy. You're gonna laugh. Chemical formula. Okay, yeah. Right? No, they do it both. So how do you determine the chemical formula?
I forgot.
Sammy, would you agree that the chemical formula would be something we should check?
But there was an H.
Because if you're going to say they're not structural isomers, that means you have to say that they
miscounted it.
So let's find out. Is there an easy way to find the chemical formula? Or do we have to really just like go through and count? Or maybe there's another shortcut we could use besides just the chemical formula to get us to feel confident they're the same. What do you guys think? Yeah, you counted it all out and you made a decision. Just structural. They can have no relationship. In the same way that methane and octane have no relationship. Different chemicals, totally. What do you guys think? So you do think they have the same chemical formula? Because you counted out all the hydrogens? Yeah. Okay. Did a lot of work. Did anybody find a shortcut? Instead of counting out all of the hydrogens, did you find another way you could do it? In addition, yeah, Maisie.
If you put the double bond on the right side, whatever. If you take those double bonds and you replace them on the left side and just bring the O to it, and then you see how many other carbons you have left, and then connect them. If you do it that way, that'd be the shortcut. Like drawing it.
You're visually deconstructing it and reconstructing it. I don't know that it is easier. It was a little hard to follow, but you were on the right track. Because if they do have the same chemical formula, you should be able in some way to restructure it. In addition to having the same chemical formula, or maybe as the result of having the same chemical formula, these two structures have something else in common. It was a term, a 3-word term, that we brought up at the beginning of the last unit. I don't believe you weren't tested on it, so you didn't see it on the unit test this weekend, but it was still something that came up in the last unit. Andy? Do they have the same degrees of unsaturation? They do. And that's the shortcut. That's where I would have gone. I can see that the ring has 6 carbons, 1 oxygen. I don't necessarily want to count all of the hydrogens, but it's actually just CH2s at 5 positions, so 10 hydrogens. On this side, on the right, I can see that I also have 6 carbons, 2 sets of 3, 1 oxygen. A little bit more work to count all of those hydrogens, but 2 degrees of unsaturation here, 1 ring, 1 pi bond. 2 degrees of unsaturation here, 2 pi bonds. So by having the same number of carbons and oxygens and having the same degrees of unsaturation, I don't have to count all of those hydrogens. I know they're the same chemical formula. And since this one was the easiest to figure out, 2 times 5, then I know that they share this chemical formula, C6H10O. Okay, so let's say that you were handed a reagent bottle and all it said on the outside was C6H10O. How are you going to know what chemical you have? Would you be able to differentiate these 2 chemicals from one another? Maybe. In my Gen Chem class, one of the first things we talk about is differentiating properties. What properties might we be able to investigate between these to see whether what one we have?
Well, the first thing that I made remember, we talked about like how linear molecules have a lot more surface area. Molecules that are more condensed, like on the left.
Well, I think we actually said that linear chains versus their branched isomers have a lot more surface area. It would be a little bit more challenging here to say which one. I'd say they both have pretty good surface area.
Okay.
But what did surface area bring us to? What property did that affect? Boiling point, melting point. So we could see look up these two chemicals and see what their physical properties are. When do they melt? When do they boil? And if they're both solid at room temperature, we can melt them and see at what temperature they melt and differentiate what chemical we have from that. If they're both liquids at room temperature, we could boil them and see what temperature they boil at and differentiate them that way. Does that seem fair? We could use physical properties. Anything else that we could use? What if I could use their bonds, the electronic properties of their bonds, to tell me the difference between these two molecules? These bonds are different. For instance, this compound on the left has a carbon-carbon double bond, whereas on the right, there is no carbon-carbon double bond, there are only carbon-carbon single bonds. Those are unique bond types. They have different properties. The compound on the left has only sp3 CH hybridized bonds. The compound on the right has both sp3 CH hybridized bonds and sp2 CH hybridized bonds. Being a CH bond is one thing, but being an sp2 hybridized CH versus sp3 hybridized CH is different. Those are different orbitals, they have different sizes, they have different bond lengths, they have different bond strengths. They're different bonds, they have different properties. Well, how can we investigate the property of these bonds? Sorry, there is one other bond I wanted to point out, and that is this has carbon-carbon single bonds, and this structure has both carbon-carbon single bonds and carbon-carbon double bonds. Distinction in those bond types as well. There's a simulator that I want to show you guys. And I have this linked on our homepage, so you don't have to work too hard to find it, although I don't know that you'll ever really go back to it. I think this demonstration is usually the only time you need to see it. On our homepage, if you go down to the very bottom link, these interactive simulations, those of you that took Gen Chem here in the last year and a half, you actually used some of these during the Lewis Structures lab. We've got this simulator that's on infrared light. Oh, pardon me. If you guys are ever bored, man, I can't encourage you enough to come to this website. You will not be bored for long. All right, let's look at this molecule of carbon dioxide, and we're going to expose it to infrared light. Oh, did you see what it did there? What is it doing? This flashlight is emitting radiation. You're seeing the photons here. But the molecule is not emitting radiation. It's absorbing radiation. It's going from a low energy state, sitting still, to a high energy state, bouncing all around, bending its bonds. Carbon dioxide is incredibly good at absorbing infrared light. In fact, the Earth takes in all of this light from the sun, soaks it up into the ground, and then starts to release it at night and during the day as infrared light. And that infrared radiation gets absorbed by CO2 in the atmosphere and then transferred from electromagnetic radiation into heat, movement. The molecules just start moving faster. So that energy that would have just transmitted right through our atmosphere and gone into space as infrared radiation is now actually staying inside the atmosphere as warmth. That's what global warming is. That's what we talk about with global warming, is that CO2 is holding onto the heat that should have left our atmosphere as light. And it's doing that because its bonds can take that exact amount of energy and transfer it into this twisting motion.
Then why does it shoot the energy back out after this? Is that just so that it
Well, you see that it does stop abruptly, so that energy, some of that energy can be emitted again.
Okay.
Now look at carbon monoxide. It's not bending, but that's because there's only 2 atoms. This is a stretching. And look at oxygen. Nothing. Look at nitrogen, the major component of our atmosphere. Nothing. In fact, do you know what molecule absorbs infrared light the best? One of the strongest greenhouse gases in our atmosphere? It's not carbon dioxide, and it's not methane. It's water. Water absorbs infrared light incredibly well. But water has a natural cycle on Earth. Water comes up out of the ocean, falls back down onto the land in this repeating cycle. Carbon dioxide, on the other hand, being emitted faster and faster without the resources to capture it and put it into new forms, changes our heating cycle. So, all of this to say, some bonds have no interaction with certain types of light. Some bonds have very strong interactions with the same type of light. We can use bonds to differentiate our molecules if we know how they interact with infrared light. So we will be diving into IR spectrometry. And we're going to look at how unique bonds absorb unique infrared light. And we'll use that as a way to differentiate our molecules. So when I showed you this molecule earlier, or these 2 molecules, you'll notice that really all I didn't even name the functional groups. So much as I assessed what bond types they have in them. That's a unique property between them, and we can dive into it. I didn't realize this guy makes it sound. Okay, there's more unique information here. First of all, this has, like we said, 5 CH2 groups. This has 2 identical CH3s, a unique CH, and another unique CH. Here we're actually looking at 2 sets of 2 identical CH2s and 1 unique CH2. What if I could use the nature of those hydrogen nuclei to differentiate these 2 molecules from each other? We'll also be exploring NMR. That's nuclear magnetic resonance. What we'll explore there is how hydrogen and carbon nuclei, we're only going to look at carbon briefly, how hydrogen and carbon nuclei give these unique spin signals. There's a lot of interesting quantum chemistry that goes into NMR. Have any of you ever been in an NMR? Have you ever been the analysis of an NMR spectrum experiment? Have any of you ever been inside of an MRI? So you have been in an NMR. The reason we don't call MRIs NMRIs is because no one wants to climb into a giant metal tube that starts with the word nuclear. But it's studying your nuclei. MRIs are applied NMRs. I mean, applied to the human body. We're looking at the signals of the hydrogen nuclei most of the time. We can also look at the signals of carbon nuclei, fluorine nuclei, phosphorus nuclei, all sorts of things. So NMR, given that it tells us unique hydrogen and carbon signals, it actually allows us to build a structure. IR tells us bond types that are present. NMR tells us you have sets of hydrogens that are all identical to each other, and they're related to each other. It can give us structural information about how these hydrogens are positioned next to each other in a molecule. It gives us a little bit less information about bond type and a little bit more information about connectivity of the structure. Two really important pieces of information that we can get out of a molecule using instrumentation. And then there's one last technique that we're going to be studying in this unit, and that is mass spec. Mass spec, like the name implies, actually studies the contributions parts of the molecule bring with respect to their mass. Because these two compounds have the same mass, mass spec would be the most challenging to use to differentiate them. But mass spec as a technique actually bombards these particles and splits them up. It breaks them into pieces, and these two molecules are going to break into different pieces, more likely than not. So we can look at their unique fragmentation patterns. We can look at the unique chunks of mass that break out of this, and we can try to differentiate them. Peter works with mass spec a lot in his research project. He studies the volatile organic compounds that are released from plants, and he takes gas samples, separates the components of that gas in a chromatography component. You guys remember chromatography? When did you do chromatography last? Today. Some of you maybe later this week, and others not at all because you're not taking the lab. That's okay. Chromatography separates components in a mixture, and then that gas chromatography ejects the components into a mass spectrum, breaks them apart, analyzes the fragments, and then compares that to a database and says this is the compound that you have in your molecule, in your mixture. So here's what I want to do first. I would like you guys to go to this website and try to find your compound, the compound that you are analyzing this semester. You can get to this website from our Canvas homepage. I'll show you how to get there. It should be compatible on mobile devices. It's just maybe a little bit harder. But if you have a tablet or a laptop, that's always the easiest. If you don't want to go to the Canvas homepage, you don't have to. You can Google SDBS, or you can Google Japanese Spectral Database. This is where we're heading, the Japanese Spectral Database. Sorry, and I did that too quickly. When you get here, you will enter this first page. You always have to go to the bottom and agree to the disclaimer. Trust me, it's worth it. This website has probably hundreds of thousands of molecules, maybe millions of molecules, I'm not sure. The funniest part is that they don't have the molecules that I would like to give you as examples on your exams, but they've got tons of real-world, meaningful molecules. So I want you to head to this website and try to find your molecule. If putting in your molecule's name here at the compound name doesn't bring it up, then you can type in its chemical formula instead, and it will give you all structural isomers present with that chemical formula, and you can try to look through it there. If you have a hard time finding it, let me know. Here's what I want you to do. This is your exercise for the next 15 minutes. Compare and contrast the IR, the NMR, and the mass spectra. By the way, spectra, plural or singular? That is plural for what word? Spectrum. So if you have Spectrum Internet, I don't know, there's not a good joke there. Each thing you look at is a spectrum. When you look at all of them, you're looking at spectra. Look at the spectra. Compare and contrast them. What do you notice between them? What features could you look for to say, okay, this is what an IR looks like, this is what an NMR looks like, and this is what a mass spectrum looks like? And talk with the people around you so that you guys can see everybody's spectra. See what they look like. Not coming up. Oh, try putting porphyrin. Oh, POR, PH. I think it's RY. Or you could look its chemical formula up. Is there? Oh, it didn't. Did you put iron in? Yeah. Don't put iron. Maybe take iron. That's good. That's what we're looking for. Yeah. Now here on the left-hand side, you've got mass, HNMR, and 2 IR spectra. So you can click through those. You're just kind of like on the overview page. So click through those to see what they look like. Nothing. I put in the four. No. Oh, yeah. Okay. Oh, if you put it in with the chemical formula, it will search both. Yeah, so you might want to like take that out. Oh, sorry. Take out the chemical formula if you just want to search the same. But did you say 4 oxygens as well? Oh, my God, I thought there were more. All right, well, then you may want to would it exist at in a flux and see how light? If you ever look at a drug that says like hydrocortisone, hydrochloric acid, it's a salt. It's a carbonated molecule. And you're just going to click through on some of those. And just compare and contrast. Look at them. Feel free to just hop around too and see what other people's structures look like. Yeah, good job. Wow. Correct. That's what I said. That's a proton NMR if I've ever seen one. Oh no, you won't. No, actually, your compound is not that bad, whereas your compound has a lot more going on to it. So we could probably break down your proton NMR. I would never ask you to break down this one. I did have when I TA'd grad school, when I TA'd Oakham lab in grad school, they had to make cholesterol in one of their labs, take its NMR, and assign all of the signals to the hydrogens. And cholesterol is a structure like this, I believe, right? Cholesterol has like a steroid ring. Oh, yeah. So it's there's a lot of things going on. It's a lot of information. Hundreds. Nice. How do you think you could differentiate? Well, yeah.
Okay, let's do the formula.
Sure. Actually, look at this. Look at the scale. Consistently, this is always going to go 0 to 12. And this is always going to go 0 to whatever your concentration is. But that's a good point. Yeah, the shape does look different for some of them. Cool. What do you? Oh no. You could try Googling it and saying NMR for I forgot what it's called. Just put like NMR spectrum for and then your compound. Not valid. No, let's go to images. I don't trust any of it. Yeah, these are a little bit different. This is a dimer, which means it's a little bit closer.
No, I have, yeah.
Dimer means 2 of the units combined. Dimer.
Yeah, a lot. I remember a lot of them.
But yours maybe because it's like what's the capitalism? What am I trying to say? It's a product that can be sold. It maybe isn't on the public database yet.
I just have.
Does that make sense? It's a drug, right? Right.
What's the
Right. So it's like proprietary information, right? Like they're gonna make it, so they might not publish it. Really? Okay. Sure. Sure. And you tried putting in the chemical formula too, yeah? Oh, nothing came up? Okay. Sorry. But luckily, you have no required assignment that's based on it. Yeah, because I can't control that aspect of it. All right. What are you looking at? What type of spectrum is this? Will asks if it's NMR. Look at your spectra that you have pulled up. Do you agree? Could this be an NMR? What would you use to decide? You said no. How come? Oh, you say I can't compare because I don't have anything to compare it to. Okay. Huh? What would you use to know? So you're looking at the units. They all have unique units. Good. And scale. HNMR is always going to go from 0 to 12 ppm. You could also look at just the vibes. First of all, these have peaks that go up. You were probably noticing on your IR that most of the peaks come down. If you didn't notice that, I'm going to try to convince you of that in a little bit. And then you can kind of see like the shape of them. It's different than what you saw in mass spec. Mass spec were these lines, just lines. These have like bases to them. They've got little offshoots. They're a little bit grainier. They're not just clear-cut lines. Good. This was proton NMR. Which by the way, when we refer to types of NMR, we often refer to the isotope that we're analyzing. When we analyze carbon, we look for the carbon-13 proton nucleus. Excuse me. That's the nucleus that we analyze in NMR. Is carbon-13. The most abundant isotope of carbon, carbon-12. So we're looking at about 0.1% of all carbon nuclei in a system when we're looking at carbon NMR. But when we analyze hydrogen, we analyze the H1 NMR nucleus. And the H1 nucleus is distinct from the H2 nucleus. You remember what the H2 nucleus is called? It's given chemical symbol D, despite still being hydrogen. Deuterium. Deuterium does not give the same signal that H1 does. And the nucleus of H1 is composed of what? A proton. So we often call this C13 NMR, which confuses people because the 13 comes first. That's where you put the mass number is top left. But we read it C13. The H1 NMR is often called proton NMR because all you're analyzing is a proton. That's the nucleus. You're looking at the spin of that proton, which is the nucleus. I think I've said this before, and I'll say it again. Hydrogen is super weird for being just a proton. Like, that's just a subatomic particle, and we named it an element. That, to me, is odd. All right, let's see if you guys can do this again. By the way, I saw on somebody's sheet penicillin, so I grabbed penicillin. I think you guys would agree penicillin is a pretty wacky structure, but its NMR doesn't really feel like it has a lot going on. It looks less crazy. Well, maybe you don't believe me yet, but it looks a lot less crazy than the structure itself. Okay, I don't know if this keeps happening to you guys, but oftentimes I have to log out or like re-sign the disclaimer to get back into it. What spectrum are we looking at here? Pretty quick. Anybody disagree? NMR, mass spec, or IR? Good. This is where I'm going to try to convince you that these are not big peaks going up with little gaps in them, but actually peaks that are coming down from the top. And one thing that I can use to convince you of that is that we're looking at here percent transmittance. 100% transmittance means nothing is absorbed. It all goes through. So I'm looking at places where light is being absorbed. What's absorbing that light? Bonds. Different types of bonds are absorbing different energies of light, very specific energies. So again, just the general vibe is a good thing to go off of, but look at the x-axis. Do you know what that unit is? Wave numbers.
Oh, I remember from the reading. Yeah.
There you go. You did your reading. Wave numbers different than ppm, although both are a unit of frequency. So unique unit, another way to differentiate what type of spectrum we're looking at. All right, one last example for you guys. Mass spec, IR, or NMR? Yeah?
Carbon.
Yeah? What tells you that?
The much broader range of ppm.
So the same unit is on the bottom, ppm, but the range is different. I was trying to trick you here. I was trying to get you to think that this was mass spec, because you'll notice that this is also pretty clean lines. These don't really have any of the jagged bottoms that proton NMR had. It's just clean, sharp peaks. But you'll notice that the unit is still ppm, and the axis runs positive to the left, just like proton NMR. Mass spec actually runs the opposite direction, 0 on the left, high on the right. When I'm asking you guys to compare and contrast, these are the details I want you to pick up on, because these are the details I'll always give you. I'll give you the units, I'll give you the scale range. You're going to be able to have an axis that you can read. So get familiar with them so that you can differentiate what instrumentation type are we using to look at this molecule. Now this exact chemical that I chose on, it actually didn't have mass spec provided, but there was another version of the penicillin salt that did have mass spec. So I'll point this out for you guys quick. This one also has a y-axis label, relative intensity. You'll notice that its x-axis is labeled M to Z. We'll talk about what that means, but it's just mass to charge. So that means you're looking at mass units here. Okay, any questions on this overview of spectroscopy? We will be able to decipher key pieces of information from these spectra in order to determine what compound we're looking at. We'll be able to take information from these spectra and we'll be able to say, I have these bond types. We'll be able to look at them and say, I have a CH3 group, or I don't have a CH3 group. And we'll be able to use mass spec in some instances to say whether we have halogens or not. To be quite honest, mass spec is an incredibly useful tool in application where you have a database to match things against. But in terms of the classroom and theory, there's not a ton of application to do. Mass spec will be what we spend the least amount of time on. There's one last instrument that I want to talk to you guys about briefly. You shouldn't have seen it on your unit test, although it actually comes up in that chapter. And this is optical activity. It's actually more appropriately called polarimetry. And optical activity doesn't tell you anything about bond types, doesn't tell you anything about the mass of a molecule. It doesn't tell you anything about the hydrogen positions and how they're related to each other. Optical activity only touches on chirality. Chiral compounds rotate plane polarized light. And we call that property of rotating plane polarized light optical activity. If a compound doesn't rotate plane polarized light, we call it optically inactive, and those are achiral and meso compounds. This idea of plane polarized light and rotating it is a little hard to describe. It's a little hard to grasp. So the analogy that I like to give is actually playing a game of catch with a frisbee. A frisbee, for the most part, exists on one plane. Light, on the other hand, although it exists on one plane, it's often being emitted from a source that is showing waves of light that take up every imaginable plane. So first we take a light source and we filter out light so that only light of one angle is coming in. This is the oscillation plane that photon has. Instead of having light at every angle, we have only this angle of light. You guys understand light is a wave, right? That is actually two different waves, the electric field and the magnetic field. So we just say, put one of those fields in this plane. Those are the photons that we're going to filter for. As you take that light that only exists in this plane and you pass it through a sample, it's kind of like throwing a frisbee through the air to your friend. That frisbee, if it interacts with nothing, should stay in that same plane until it reaches your friend, correct? Unless it hits a little bit of wind and it gets tipped up like this, and now it hits your friend actually at a different angle than it left you. That's what these chiral compounds do to light. As the light passes by the chiral compound, because it's not being absorbed by the compound, it's not the bonds absorbing it, it's just passing by it. As the light passes by the compound, something about its asymmetry causes the light to be pushed and pulled in certain ways that it ends up at a different angle. Isn't that just weird? It is, I think, similar to this process of wind blowing your frisbee. It's not having a very strong effect on it, but it's noticeable. This compound that's chiral is shifting your light. So in a polarimeter, you know what angle your light is coming at. You have a detector that measures what angle that light is hitting at. And then you can calculate that difference in that angle of rotation. So you can use optical activity just to say, this is chiral, this is not chiral. But there's this even stranger property. In enantiomers, rotate light equal and opposite directions? If R, 2-bromobutane, rotates light 15 degrees clockwise, then S, 2-bromobutane, rotates light 15 degrees counterclockwise.
So it's literally like rotating a mirror.
Their rotations are mirror images of each other.
It's literally like
Correct.
rotated a mirror.
Correct.
Yeah.
Which means that if you have an even mixture of the two of them, if you have 50% one enantiomer and 50% the other enantiomer, how much will the light rotate? Half the molecules rotated this far, the other half rotated this far. That cancels out. We call this a racemic mixture. It's also sometimes just referred to as a racemate. And racemic mixtures were first discovered by Louis Pasteur. Pasteurization, also Pasteur. Pasteur pipes, the glass pipettes you have in lab, also Pasteur. Pasteur noticed that racemic acid, which was a known compound at the time, would form these salt crystals that had spirals to them. And that if left to form at a very stable way, those crystals would actually form in opposite spirals. He noticed that these chemicals were mirror images of each other and had mirror image properties. And then looking through optical activity, you could see polarized light had these equal and opposite effects. So this is an important term. We're going to use it later in the semester when we talk about reactions, because some reactions will produce racemic mixtures, 50-50 enantiomers. Diastereomers have no related effect. Meaning you can't look at two diastereomers and say, well, if this one rotates plus x degrees, this one rotates minus x degrees, or minus x squared degrees, or whatever. You have no relationship between them. They are not the same molecule. There is some math that gets in here. If you have like a 10-90 mix of enantiomers, that 10% of one cancels out 10% of the other, and you get 80% of the expected rotation that's left over. And we can use that for what's called enantiomeric excess calculations. I'm not going to have you go through those calculations. But you can actually use optical activity to figure out how pure is a sample. Do you have just one enantiomer? Do you have a 50-50 mix? Do you have somewhere in between? I'm so sorry. There was one more thing I wanted to say here. Maybe there's not. With that, I'll let you guys take a 5-minute break. And if I think of it, I'll come back to it. Why don't you guys get up? Even if you're not going to move, get your blood flowing.
We're also we're prime species, so we can run one of those greenhouses. Yeah, for sure.
Hello.
That was so mean. I almost started laughing because you pulled a knife at me.
Good. No, actually, two things. Two things have to be different. Or you want to look for two things for a diastereomeric relationship. One chiral center changes, one chiral center stays the same. At least. How many chiral centers?
Yeah, I bet.
It's just the one. So can those two things be true? There's only one chiral center. Can I leave one chiral center flipped and one chiral center the same? So a compound that has only one stereocenter, only one chiral center, has only an enantiomer, no diastereomer. Meso compounds, on the other hand, like plane of symmetry, no enantiomer. Because if I flip it, it is its mirror image. But it has always a minimum of 2 diastereomers. So, not all chiral compounds have enantiomers, but all chiral compounds. No, I said that wrong, sorry. Not all chiral compounds have diastereomers, but all chiral compounds have enantiomers. No meso compound has an enantiomer, but all meso compounds have at least 2 diastereomers. Great. Thank you, but I'll pass. My chocolate shake wouldn't go well with the mint, but I appreciate it.
Yeah.
Are you trying to say something about my breath?
No, I was like, it's gum time, so let's all have gum.
Oh, I appreciate that. Oh. I'm sorry, why did it take so long then?
She was drawing what's older.
Oh. You were drawing the new stuff before the old stuff? It's okay. It's recorded too. It's on the internet forever. I have a student at my Oakham too that will come in late occasionally, only like 5-10 minutes, and then he'll go at the end of class. And you guys know how I'm like packing up to leave at the end of class. What notes did I miss in the beginning of class? honestly, I don't even know anymore. After a 2-hour lecture, I couldn't tell you. And I'm like, but it's recorded. He's like, I don't want to watch the recording. Oh, I'll delete it. Don't worry. You don't have to watch it. Sorry. I'm sorry you have to spend 5 minutes watching the recording to get the notes that you made.
Something that I will never forget in my entire life as long as I live is when I went to my 7th grade English teacher and was like, hey, I'm sorry I was not feeling super well yesterday. And it comes out of my mouth because I'm that sick of it. Did I miss anything? And he's like, well, you did.
No, we just hung out saying songs yesterday.
And we were like really good. We were really close. So we weren't like she wasn't like a bad teacher. Like I didn't
Yeah.
feel like a bad teacher or anything. But like I learned that day like that was not how I should have worded it.
Yeah.
So ever since then I've always been like, what did I miss? Not did
Yeah.
I miss anything.
Yeah, I know it's always awkward communicating about absences because
Yeah.
you want to ask so that you can express that you're trying to do well in the class, but you don't want to annoy. All right, I remembered what I was going to say. This rotation that I just erased, where we say that compounds rotate light clockwise or counterclockwise, we say that's either plus or minus. And we actually relate these to each other. We say that plus is an R compound, not an R chiral center. It's terrible, but it all comes from the Latin rotisserie chicken or something. I always forget the Latin, but it has something to do with R. If it rotates it counterclockwise, if it rotates at a negative angle, we call this L. Oh, you know what? I'm second guessing myself. I'm sorry. Yeah, I want to check that it's actually L and R. I'm pretty sure it's L and R. I will come back to that. And L has something to do with laboratory. I don't know. I can never remember. So these are a series of structural isomers. And you can see that their names don't describe the absolute configuration of their compounds directly, of their chiral carbons. They don't say that carbon 1 has this absolute configuration, 2 has R or S, 4 has R or S. Instead, it's just named menthol, isomenthol, neomenthol, neoisomenthol, which actually gives you an idea of the relationship of all of the chiral centers. And then it's given either plus or minus, meaning which enantiomer you're looking at. Look at how the methyl and hydroxyl group are both wedged, but the isopropyl is dashed. Its enantiomer, methyl and hydroxyl are both dashed, isopropyl is wedged. They're both menthol. One is plus, one is minus. They're enantiomers of each other. Having a positive rotation or being labeled as an R enantiomer has nothing to do with any of the chiral centers, because you'll notice I can change just one of those chiral centers and I can still rotate light positive. I can change another chiral center and I still rotate light positive. I can change two of the chiral centers again and still rotate light positively. So there is no relationship between plus and minus with R and S chiral carbons. It gets really confusing to try and say, oh, if I have a plus enantiomer, what is the absolute configuration? You don't know. You can't know. They're not related. You can analyze a compound and know I have the plus or the minus enantiomer, but you do not know how it's arranged in space. That's the short of it. All right. Any questions on optical activity? before we move on from it. What you will need to know how to do around optical activity is look at a compound and say, it is optically active, it is not optically active. And how do you determine that? It is chiral, it is achiral. That's it. All right. I have had bonus problems in the past where I give information, structural information like IR and NMR information, and additionally, I put some optical activity in there so that you can see if I'm giving you a chiral molecule or not. So that's the usefulness of it. If you see it, optical activity, and it says plus 37.1 degrees, optically active. That's all it tells you. You don't need to know what the numbers mean. It's just experimental data. Okay, something to mention about this next section, this unit. I had a conversation on Thursday with another of our organic professors. I usually teach this unit similar to the way, I always have. I usually teach mass spec first because I can finish it in a lecture period or a lecture and a half. And then I do IR because I can do that again in like a lecture period. And then I like to save NMR for the end because it takes like 2 lecture periods to really get it down. But NMR is by far the most powerful of the tools that we'll learn and the most involved. So I was convinced to actually flip this, and we're going to start with NMR today and come back to look at IR and then do mass spec last, since it is the easiest and kind of the least impactful. I'd rather you have the most time to sit on and absorb NMR. I recognize that means you maybe have done the pre-reading for just the IR and the mass spec, and you haven't done the pre-reading for the NMR. I'm also going to have to go into active and change those due dates. So I apologize for the last minute change to plans. But trust me, I think that this is giving you more time to master the more challenging technique rather than just teaching it to you next week and then sending you off to your unit test. Sound good? All right. Let's dive in more to nuclear, magnetic resonance. When I was in college, I took a spectroscopy course. It was a higher level chemistry class where we got into the nitty-gritties of spectroscopy. Because of that, I have some perspective of how much you need to know and how much you do not need to know. So I may oversimplify things for the sake of not getting too technical and making things a little bit easier to understand. If you are curious to understand it better, there's so many resources out there for you. But for what we're going to do in class, we're going to try and keep it simple. First of all, it's important to know that only some nuclei can be studied. Not all nuclei are NMR active. They don't all respond to this technique. Even some that are NMR active, they give off very different signals. You guys saw our scales earlier. They don't necessarily fall on those scales. So even if they gave something, you wouldn't necessarily know it's there. By the way, we just got a new NMR downstairs in our OChem lab. So those of you that are in OChem this semester, you've seen that big box that's in the back corner. That is an NMR instrument. It's pretty powerful. It's actually not that powerful, but it is way better than the NMR we used to have. We never even used that old one because it just wasn't good. Here are the nuclei that we're going to study. H1, proton, and C13, carbon, often called carbon 13. You can also study fluorine nuclei. I did an experiment when I was an undergrad analyzing fluorine nuclei for a synthesis that I was trying to do. These have very different scales. These give a signal. I want to kind of keep this in the same range. These give a signal that range from 0 to 12 ppm. And for our carbon-13 NMR, we see a range. You will see it all the way from 0, but it will look more like the lowest signal is ever at about 20, up to about 200, maybe 250 ppm. Different ranges. Oh, and then there's one last component here, which is their percent abundance. When studying the H1 nucleus, we're looking at 99% of all hydrogen nuclei. Actually might be closer to 99.9. I think it is 99.9. So when you have a sample that has 10 hydrogens, 99.9% of all of the molecules, all of the hydrogen nuclei in all of the molecules are going to give you a signal. What that means is that this gives very loud, very clean signals. It's easy to analyze it because there's a lot of nuclei giving that signal. Carbon-13, on the other hand, makes up about 1.1% of all carbon nuclei. So for every 100 atoms of carbon, you've got about 1 carbon that's actually giving a signal. We could do some Gen Chem, like Avogadro's number type math problems here, and we could figure out 10 milligrams of a sample is how many moles of that compound is how many atoms, and then figure out how many of those carbon atoms would actually be nuclear NMR active. Carbon-13 is harder to get readings on because it's less abundant. Its signal is less loud. It's less clean. The signal is just messier. In fact, I used to never teach carbon-13 NMR until we got our new NMR downstairs. Reason being, when I was in grad school, the cost to run carbon NMR was way higher than running a proton NMR. It was much more expensive. You had to run it for like 6 times as long as you would run a proton NMR just to get good data. So you didn't run a carbon NMR unless you really needed to. And now the NMR that we have downstairs, which is not as powerful as the NMRs I used in grad school, can collect a carbon NMR very easily. So I don't know if the technology changed in the last 4 years, or maybe we're just getting lied to down there, but now we're going to teach it because it's actually easier to understand than proton NMR. And we'll be able to look at it pretty easily. Okay, here's the setup. We place the sample in a magnetic field. In physics, you'll abbreviate a magnetic field with this B line. Those nuclear spins will align with the magnetic field. So if I imagine my compound looking something like this, and these are their nuclear spins. They're just kind of random. They go all over the place. You guys remember that we show spin with arrows, spin up, spin down. But here I've just got like these nuclei are just kind of oriented randomly. They're in a low energy state. They're in their low energy state. And then we align them with the magnetic field, and we can get all of these nuclei to align their spin. Low state or high state?
Well, if we're forcing it to be that way,
Right.
it's not like a high state.
If I just went from a low state, a ground state, and now I'm changing it, I'm in some sort of excited state. The magnetic field is exciting the nuclear spin. Woohoo! All right, now we turn off the magnet. And the nuclei relax through radio wave emission. That's their resonating frequency. We listen for the radio waves, except radio waves are light. So we look for the radio waves. Do you guys know your cars are looking for radio waves? They're not listening for radio waves. That's always the trippiest thing to me. Radio waves are light, so you have to see them. And this is where we plot them. We look at these radio waves, and we transform them from a frequency domain, from a time domain. We look at the frequency of the wave and how it dims with time. We do mathematical functions on it, the Fourier transform, and we take it from a time domain signal to a frequency domain signal, and this is where we plot the units of ppm. ppm is often used to measure what? Ratio. ppm stands for parts per million. Parts per million, parts per billion would be a similar one. But parts per million is used as a unit when reporting often concentrations, right? You don't want lead in the water to be above a certain parts per million. You don't want, I can't think of any other example off the top of my head. We use it for concentrations. But here we're actually using it for frequency, and that should be valid, right? Parts per million, that is a unit of frequency. How many times does it show up per 1 million times? That's frequency. So this is what we look for. On the y-axis, we get relative intensity. Sometimes relative intensity is a meaningful measurement. In this case, relative intensity is not necessarily meaningful because we're going to see how there's a lot of other factors in the height of a signal. So relative intensity doesn't really tell us much. ppm is going to be really useful. Okay, that's pretty much it. We're going to learn how to decipher the signals that show up on that scale. And we're going to use it to understand more about our compounds. The rest of what I want to talk about all has to do with proton NMR. We'll come back and reiterate similarities and differences with carbon NMR. But first, the three major parts of a proton NMR signal. The first is its chemical shift. This is also written as the lowercase delta. Remember, that's the same symbol that we use for like partial positive and partial negative. And it's given the units ppm. Oh, okay. Chemical shift is just where along the x-axis the signal shows up. That's all that chemical shift is. Well, I actually have designed this correlation table for you guys. It correlates where the chemical shift is with what functional group you can expect produces that signal. And we can say that. We can say correlates, and I'm actually going to put approximately, because there is no part of this science that can't be done without a little bit of hand waviness. Approximately correlates to the functional group. There's some terminology I'm not so interested in having you guys know. Like, I'm not going to test you on this, but you may see this in some places. Close to 0 ppm is called upfield, and the further down you go to the left is called downfield. I don't have a good way of remembering which way is upfield and which way is downfield. I'm not much of a sports guy, so this might only make sense in my head, and if you actually understand sports, it won't make sense.
Maybe if you just like flip the graph 90 degrees.
I think of hitting a baseball downfield. Do you hit a baseball downfield? You can. Good. So the 0 is to your right, so the further away from 0 is down the field. That's where we're going from. I will typically say shift more left, shift more right, rather than saying shifted more downfield, shifted more upfield. But that is some terminology you'll see in some places. Okay, roughly it correlates with functional groups. Now there's some nuance to what I've tried to put in here, because you'll notice that there's some overarching range and ranges that actually overlap with each other. If you have an alkane carbon, an alkane hydrogen, because we're only looking at signals from protons, the less substituted it is, the further right the signal shows up, and the more substituted it is, the further left the signal shows up. Until you get to a point where it's not alkane. This I call the functional group adjacent, because it doesn't matter what functional group it is. If a hydrogen is adjacent to a benzene ring, if a hydrogen is adjacent to an alcohol, if a hydrogen is adjacent to an ether from the oxygen linkage, or adjacent to an ether from the carbonyl side. Those are both functional group adjacent. And all of those signals show up, for the most part, in this region. Again, some nuance. A hydrogen that is closer to a heteroatom, like this hydrogen, which is hydrogen, carbon, oxygen, its signal shifts more left, which is why it's on the left side of this structure, because this signal would show up on the far left end of this range. Whereas this hydrogen, which is hydrogen, carbon, carbon, oxygen, it's further away from a heteroatom. Its signal actually stays further right. And I'd like to say that it's the electronegativity of these atoms that causes the shifting in these electrons, the shifting in these signals. But it actually has something to do more with a property called shielding. Why are nuclei affected by a magnetic field? Anybody want to give it a shot? Why are nuclei affected by a magnetic field? There you go. It's the electromagnetic force. Those positive charges in the nuclei, the protons, are impacted by magnetic fields because of the electromagnetic force. Okay. What else is affected by a magnetic field in a molecule? Electrons, yeah. So the more electrons that surround a nucleus, the more a nucleus is protected by electrons from the magnetic field, the more shielded it is. And the less a nucleus has electrons around it, the more de-shielded it is. So a hydrogen that is closer to a heteroatom, its electrons are being pulled away from it. It is being de-shielded. A hydrogen that doesn't have any electronegative atoms around it, less de-shielding. There is some crazy things that goes on. It's not just electronegativity. Like pi bonds and aromatic rings, they have some really interesting ways to create a counter magnetic field, and that disturbs nearby electrons and nearby protons as a result. So any functional group that's adjacent to a proton changes that shift, whether it's a heteroatom or not. Okay, that's what this shielding and de-shielding is. Shielding more electrons nearby. De-shielding, electrons are pulled away. Literally, shielding from the magnetic field. If you wanted more proof that aromatic rings are not alkenes, look no further than the way they impact chemical shift. Aromatic rings often have signals ranging from 6.5 to 8.5. I have to say often because they can go beyond or fall short. Alkenes often have these signals ranging from about 4 to 7. Some overlap there. But if alkenes were truly a part of aromatic rings, then they should have the same effect on hydrogen signals. They should produce the same chemical shift. But they don't. They're different functional groups. They have different chemical properties. They have different electronic properties in a magnetic field. And then the most distinct group, well, actually, to be fair, the most distinct group to me is the aromatic ring. That is a region I always look for to quickly decide if there's an aromatic ring in the structure or not. but one of the most distinct groups, the aldehydes and the carboxylic acids. They kind of share this range from about 9 to 12. But if you had to guess, more often than not, whose hydrogen shifts further to the left? Don't feel like you need to guess too hard. Lean into the nuance of how I set up the molecules. Whose signal shifts further to the left? No? I thought you were going to say. Yeah. Why? Okay, that's good. But also, it's on the left-hand side, which is what I'm trying to tell you. Carboxylic acids shift more to the left. Aldehydes shift more to the right within that range. But you've got this good point, which is this hydrogen is directly next to an oxygen and then a carbonyl, whereas this hydrogen is connected to a carbon first before the carbonyl oxygen. All right, so this is a confusing thing for you then, because you'll notice I haven't put a couple of hydrogens that are important parts of functional groups on here. In fact, I might encourage you, if you download this, to study off of it. If you print this off to use on your unit test, you might want to annotate it. Put some more detail into this. And here's something that you might want to put. Alcohols and amines they have a chemical shift for their hydrogens about 0.5 to 5.0 parts per million. At least given what you just said. Carboxylic acid shifts further because it's got more electronegative. Does that surprise you? Here's that range. That range for an oxygen bonded directly to the, did I say that wrong? For a hydrogen bonded directly to an oxygen, it shows up even further below a hydrogen that's adjacent to an oxygen. This should feel pretty weird. In fact, this trips up a lot of students on test questions. They'll look at a spectrum and they'll say, oh, I've got an OH in the molecule. That's going to be whatever the furthest down signal is. It's going to behave like a carboxylic acid. It doesn't. It behaves a little bit more oddly. It behaves like an alkane or like a functional group adjacent. It doesn't even get pulled down as far. It's not as de-shielded as an alkene hydrogen, a vanillic hydrogen. Odd, correct? Very odd. What do you think could be accounting for some of this extra shielding, despite the fact that it's bonded to a very electronegative atom, has a very strong dipole? OH, NH groups. What could give shielding back to them? When you analyze a molecule in NMR, are you analyzing one molecule? What are you often analyzing? A sample, a collection of molecules. Maybe a small amount, right? 500 million molecules, maybe 600 billion million molecules. Just a small number. A lot of molecules in a very small sample. What is that? Hydrogen bonding between OH groups. Hydrogen bonding between NH groups. How would that affect shielding? Would that increase shielding or would that increase de-shielding? Would that further de-shield the proton or would that re-shield the proton? It's gotta be, right? You're stealing electron density from this hydrogen because of this oxygen it's bonded to. Okay, well, I'll give some electron density back from this oxygen. This kind of explains the odd properties. It doesn't do a perfect job because then you might argue, why don't carboxylic acids also hydrogen bond and re-shield their signals? Okay, you got me there. I don't have a good answer for that. But if that lets you sleep at night, good. I know, it's letting some of you sleep right now. Okay. First component of a chemical signal, chemical shift. We have two more, but here's what I want to do. Instead of trying to just get into those other two, because we won't really get through them, I want you to look at this structure, this spectrum, and I want you to tell me what types of hydrogens do you think it has? And I know my correlation table is on the other page. You guys might not have your correlation tables up. Maybe I can do this. Can you decide what types of hydrogens there are in here? Raise a hand. Name one off. You think there's some alkane carbons in here? Alkane hydrogens. Got a signal around 1.5. The only thing that really produces that type of signal, alkane hydrogens. Okay, anything else? Functional group adjacent. Do you know whether it's adjacent to an ester, an amide, an alkyl halide, an aromatic ring, a ketone, an ether, an alcohol? No. No idea. This is the most vague part of NMR. It's that region right there. And how many of those signals? Well, this signal here is probably functional group adjacent because it's before 4 ppm. This signal here could be functional group adjacent, could be vanillic, but then we've got this other problem of all three of those signals on the right. Do we know yet if they could be alcohol or amine signals? We don't really have enough information. We're going to learn more about the shape of those signals and how that actually rules out two of them from being alcohols and amines. But for all we know right now, based on chemical shift, could be functional group adjacent, could be vanillic, could be alkane, could be alcohol and amine. A little bit hand wavy here. There's this approximate correlation. What else? Aromatic, 7.5. That's clear as day. That's got to be our aromatic ring. And how about this one at 5.5? Might be vanillic. Vanillic, you guys might remember we introduced a nomenclature term called vinyl. And vinyl was when a carbon-carbon double-bonded group came right off of a carbon chain. And this is vinylic. It's a hydrogen that's a part of that alkene. That's all that's coming from. It could be, but here's a challenging part about chemical shift. And this would make a good last point under chemical shift. all of these different groups, they have compounding effects. In fact, the hydrogen in the very common organic solvent chloroform is often used as a solvent for NMR. Chloroform is functional group adjacent 3 times. It's adjacent to a chlorine, and a chlorine. If it was adjacent to just one of those chlorines, I'd expect its signal to be here. If it's adjacent to 2 of those chlorines, I might expect its signal to be here. But being adjacent to 3 chlorines, that hydrogen has functional group adjacent compounded on itself. The actual signal of that hydrogen is at 7.26 ppm. What would you expect to produce a signal like that? An aromatic hydrogen, an aryl hydrogen. So when I say there's hand waviness to this, there is. These are good approximations, but you have to look out for those compounding effects too. All right, now let's take a look at the actual structure again. This was penicillin. Okay, good. We have aromatic hydrogens. That's what we saw around 7.5. All of these aryl hydrogens. We have alkane hydrogens. Here's a CH3. Here's a CH3. That's good. We have an NH. And we don't have enough information based on what we've learned yet, but that NH is most likely this signal at 4.2 because it's nice and clean. We'll talk about that one later. All right, here is functional group adjacent twice. Here is functional group adjacent twice. Here is functional group adjacent twice. And here is functional group adjacent twice. So looking at the remaining signals, there are no vinylic hydrogens. There's no carbon-carbon alkene with a hydrogen coming off. So this signal at 5.5, it's not vinylic. It's the result of some compounding effects. And then we can just say that this other signal here, also functional group adjacent, because that's the only other type we have. All right, that's your taste test of NMR. When we come back, we're going to look at integration and splitting pattern. We're going to look at the shape, and we're going to look at the area underneath the curve, and that will wrap us up for NMR. Maybe we'll be done Wednesday. Maybe we'll pull it through next week. We'll see. Have a good night, everybody. I'll see you Wednesday.